So what is the slope of the line tangent to the graph of this function at x equals 2? Man, this is going to be great. But as I look at this, I'm coming in from this side. I wonder what the slope is at that point. Okay, I am pointing at an open circle. Wonder what the slope is coming in at that point. That point doesn't exist. Now, I know you could say, oh, but it's up here, sir. I hear you. We can find the slope here, and that slope there is actually 1. But the slope here, is it 1? Actually, it is. But does it matter? No, because we have discontinuity. How can I talk about the slope of a point when there's a lack of continuity? Let's think about it this way. And this is the way I usually describe it in class. Going back to some previous problems. You're driving on a road. Vroom. There you go. Wasn't that a pleasant ride? How lovely. Vroom. Okay, let's keep driving. Vroom. Vroom. Okay, you hit a pretty sharp curve there. You hit a very sharp curve there. Now, this is not the mathematical definition, but if you hit a sharp curve, and I don't mean a curve, I mean a point, a jagged point, to where you would start fishtailing and your back wheels are just going crazy and you're spinning and, you know, it's all like Fast and Furious. No, then you have a point where the derivative doesn't exist. So, vroom, you're squalling, vroom, all right, vroom, no. Now here, it was pretty smooth. Straight line, straight road, vroom, and then just transitions into curvy, and you never even knew it. But here, y'all, the bridge is out. Don't even try driving across that. So I can do the whole left side, right side, do they match up, all that beautiful stuff. Don't waste your time. Do not waste your time. F prime of 2 is undefined. Because the function is not continuous at x equals 2. There you go. Okay, what is the slope of the line tangent to this graph at x equals 0? Well, we don't have a piecewise function. And I can drive that, and I can be like, vroom, oh man, smooth road. So maybe it works. Maybe it does. Let's see. Oh, I grabbed the purple pen. Should I try it? No. Let's go blue. Let's do the limit as x approaches 0. Now, I'm not going to go left or right because it's one piece of cube root of x minus, and then we're going to plug a 0 in and have the cube root of 0. Divided by x minus 0. So, okay, a lot of obvious things that I can do here. First of all, cube root of 0 is 0. X minus 0 is just x. So this is the limit as x approaches 0 of the cube root of x. I'm going to rewrite that as x to the 1/3, and we have an x in the denominator. Okay, let's keep working on this a little bit. We can subtract exponents. There's a 1 here. 1 minus 1/3 is 2/3. That goes in the denominator. So x to the 2/3. There's a 1. Okay, let's plug 1 in. Sorry, let's plug a 0 in for x. If I plugged a 0 in for x, I'd be dividing by 0. So this actually does not exist. So this limit does not exist. Therefore, I'm writing my answers in red. G prime of 0 is undefined. Undefined. Okay, but it was so smooth. I can drive my car across that. Yeah, you can. Sure. Whatever. You give that a shot. See how that works. Okay, if we were driving and this was like you're driving and you're not driving on this road, you're driving here, you've reached a sheer cliff, right? Like if this was a surface and you're driving, you've reached a sheer cliff. If you notice, if I drew a line that represents the slope at this point, then I would be drawing a vertical line. That is an undefined slope. Okay, so we have a little bit of stuff to write. Oh, what color shall I use? I'll use black. I'm not going to brave the purple pen. I don't know, it might give out on me. Differentiability implies continuity. If a function is differentiable, that means I can find the slope. That means the slope exists. Then the function is definitely continuous. Let's write all that down. If a function has a defined slope at x equals c, then it is continuous at x equals c. Okay, let's talk about this for a minute. Every example that we've done so far where we had a slope, we had continuity. So there's definitely a connection there. So if this is kind of a however, if a function is continuous at x equals c, then it is not necessarily differentiable. I ran out of the box. At x equals c. Okay, all right, so let's back up and talk about this again. We had two ideas. Here's one idea, here's the other. If a function is continuous, then it's not necessarily differentiable. Okay, this function was continuous, but I couldn't talk about the slope there because the slope was undefined. The function was continuous, but you squalling tires. Function's continuous, but squalling tires. The derivative, the slope at that point, was sharp. We couldn't talk about the slope at that point. It wasn't a smooth curve. But every continuous function isn't necessarily differentiable, but every differentiable function was continuous. Like I could find the slope here and the whole thing was continuous. How lovely. I could find the slope here and the whole thing was continuous. How lovely. I could not find the slope here, but it was continuous. So if the function's differentiable, it tells me it's continuous. If the function's continuous, it doesn't necessarily mean it's differentiable. There are going to be examples that you'll be asked for probably, where it'll say, give an example of a function that is continuous but not differentiable. Perfect examples of that would be absolute value or something like this. So in red, just to make it stand out, if a function is continuous at x equals c, then it's not necessarily differentiable. Notice that's continuous but not differentiable. Or this one, continuous but not differentiable. That vertical slope right there. It doesn't.